Dr. Jack Zhu is the author of many WebGPU books. In this course, he will teach you the basics of WebGPU.
Hi, I'm Jack. From this video, you will learn the basics of WebGPU graphics programming by building 10 separate WebGPU projects. Each project will be created on top of the previous one, from simple primitive to complicated 3D graphics. Our end product will be a beautiful 3D Sinc Surface, as shown here. We will create these WebGPU projects from scratch and show you how to add 3D graphics with GPU acceleration to your web applications. Here, I want to thank Bo and freeCodeCamp for publishing this video. freeCodeCamp is a great resource for the programming community, and thank you for all that you do. Before getting into this video, I'd like to quickly tell you a little bit about my background. I got my PhD in theoretical physics and have over 25 years of programming experience in C, C++, C#, .NET, and web development. I have published over 20 books about practical programming on a variety of topics, including graphics programming, machine learning, quantitative finance, numerical computation methods, and web applications. Recently, I created a YouTube channel, Practical Programming, based on my books. In this channel, I will present several step-by-step video series in which I will emphasize the usefulness of example code to real-world applications. The first video series is about WebGPU graphics programming. That is based on my recently published book, Practical WebGPU Graphics. The project presented here are also selected from this book. My channel, Practical Programming with Dr. Su, is new and I plan to update it every week. I would greatly appreciate if you can check out my channel and describe it. Now let's go to WebGPU graphics programming. Now let's start project 1, set up a development environment. The source code used in this project can be downloaded from the GitHub link here. This project uses this specific version. So now, what is WebGPU? WebGPU is the next generation graphics API. It is a future web standard for graphics and compute. WebGPU will provide the modern 3D graphics and computation capability with the GPU acceleration. In this video, we will use the following development tools to build our WebGPU applications. First is Visual Studio Code, Node.js. We will use TypeScript as our programming language, and we use Webpack as our modular bundler. In order to run WebGPU applications, currently we have 3 options. The first one is to use Chrome Canary to test our WebGPU applications. The other option is to run WebGPU applications on a regular Chrome through Orange trial. Starting from Chrome 94, WebGPU is available as an Orange trial in the regular Chrome. You need to register to Orange trials and request a token for your Orange. The third option is that Chrome will officially support WebGPU in May of this year. So after this May, you will be able to run your WebGPU applications on a regular Chrome. In this video series, I will use Chrome Canary to test our WebGPU project. Here I suppose you already installed Visual Studio Code, Node.js, and also installed TypeScript globally on your machine. Let's start programming. Now let's open a command prompt window. Let's make a folder, make directory GPU app, and cd into it. And then we are going to run this command npm init y to create a package JSON file. Okay, this file will store our dependency used in this project. Now we are going to install Webpack and its command line interface. Use this command npm install li. Webpack is a modular bundler that bundles relevant files together to generate a static asset that can be used by the web applications. Here we use Webpack mainly for transpiling TypeScript file, but here we don't use it to bundle other type of files such as HTML and image files. Now installation is complicated. At this point, we are going to start Visual Studio Code with the command code period. Here is the Visual Studio Code interface. You can see we only have package JSON file, but not much happening here. Now open a terminal window by pressing Ctrl+J key. Now let's install some dependency packages. First, we will install jQuery and the corresponding type package. npm install jQuery. We will use jQuery to manipulate the DOM elements in our applications. Next, we want to install styling, CSS, and TS loaders. In case if our project contains styling sheet file, we need to use a style loader and a CSS loader to bundle it. In order to create TypeScript modules in our project, we also need to install TypeScript locally. npm install TypeScript locally. We already installed it globally before. Now open package.json file. You can see the script section here only contains the test attribute. That is not very useful. Here we are going to replace this section with the code. Here the code allows you to run Webpack in different modes like development, production, and watch mode. Now we can save this file and close it. Now all the installed packages are going to be stored in the node modules folder. Here, the package lock JSON file is automatically generated for any npm operations, so we don't need to do anything with it. Next step is to initialize TypeScript file with the command tsc-init. This operation creates a configuration file for TypeScript called tsconfig here. Now we open this configuration file and we need to replace its content. You can see here we set the target to the ES6. Also note we define the root directory as src and output directory as dist, the distribution folder. Now save this file and close it. We then create some folder structure for our project. First, let's create the src folder. So here we create a folder called src. We will store all the source file in this folder. Next, we create a dist folder. dist, which will contain all files that will be uploaded to the web server for running our applications. In this folder, there is at least one HTML file. Let's add index.html file to this folder. Add another file, index.ml, and add some code to it. You can see here we add the title WebGPU project. Here, H1 title check whether your browser support WebGPU or not. We also have a H2 DOM elements here and set its ID equal to ID GPU check. These H2 elements will be used to display a text string that will be returned by a TypeScript function, which will be created later. Now we are about to finish the development environment setup, but we have missed a key step. That is, we need to install the WebGPU package. WebGPU working group have created a type definition for WebGPU standard. This package matches the work in progress WebGPU API, which is currently not very stable, so it can change almost weekly, so be careful to use it. Anyway, let's go ahead to install it with this command. So here we specify the version 0.1 and 12. This is the latest version to install it. They call it WebGPU tabs. Because WebGPU is not backward compatible, so you better use the same version to run our project. Otherwise, you need to do some modification to your code to run application. So I suggest you use the same version here, 0.1.12. After installation, we need to configure it. Open TypeScript configuration file. You can see here we already configured it. We add WebGPU tabs and a node in the tabs section here. You can see here we have a node, the tabs. So we need to install it. Use this command to install this node tab. Okay, the WebGPU is now available for our project. Now let's add some TypeScript file to our project. First, add a new file called helper.ts file to src folder. So we add a new file called helper.ts file and add some code to it. You can see here we use this navigator.gpu variable to check the GPU availability. This variable is defined in the WebGPU API. So you can see here we use the fed arrow to define the TypeScript function. Next, we need to create an entry point file called main.ts file. Okay, save this file first and close it. Let's add another new file to the src folder called main.ts file. Now add some code to this file. So we just import the jQuery and also import the check WebGPU function from help.ts file. We just implement. So here we define ID GPU check to display the string returned by check WebGPU function. Here the ID represents H2 DOM element defined in the index.html file. Make sure this ID is the same as the ID defined in that file. Next, we also need to create a Webpack configuration file. Now add a new file to the root directory webpack.js file. You can see here we define the bundle output directory as drst, and the entry point is named main here, the main src main.ts file. Note that the output file has always with bundle.ts extension. Now we can save this file and close it. Now we can run the following command from terminal window to bundle our TypeScript file. npm run prod in the production mode. Okay, finished. You can check the bundle file in the drst folder. You can see here we have several main bundle.ts file. This is our bundle file. This is lesson file. This is source map file. This main.bundle.js file has been referred in the index.html file. You can see here this main bundle.js. This bundle file generated by Webpack. In order to test our application, we also need a server. Here we will use the live server extension. Click on the extension link, search for live server. This one, the first one, live server. Here I already installed Otherwise, we have an install link here. If you haven't installed it, just click install the button to install the live server. So I suppose you already installed it. Now we can open index.html file, right click anywhere, open with live server. Click this link. This will open our default browser to display the web page. Unfortunately, if your default browser is regular Chrome, it will display the message. Your current browser does not support WebGPU. So in order to run WebGPU application, here we will install Chrome Canary. So here search for Chrome Canary. Click it. So this nice build for developer. Just download the Chrome Canary and install it. I already installed this Chrome Canary on my machine. Please remember the location where your Chrome Canary is installed. Okay, I suppose you already installed it. Let's go back to Visual Studio Code. We want to change the default browser to Chrome Canary, which will be easy to test our WebGPU application. So press Ctrl-Shift-P and type the preference open setting here, JSON. So open this file. Here, you need to add this 3 line here, the live server setting. Don't show info message. Oh, I set it to true. This doesn't matter. I also set the root directory as dist because our index.html file in this directory. So this advanced customer brochure command line here define the default brochure. So you need to replace this code. So you need to copy your Chrome Canary exe file location and paste it here. You must change it to match your situation. Now we can save this file and close it. Now start Chrome Canary and type Chrome flags and search for WebGPU. Here, enable it. Here I already enable it. So if you not, you just need to enable it to make WebGPU available for our Chrome Canary. Okay, we can close it. Okay, finally, we can test our development environment for WebGPU applications. Here we have a link on the status bar area. You can see Go Live link. This time it will start Chrome Canary brochures. Click this link. You can see, great, your current brochure supports WebGPU. Congratulations, we have successfully set up the development environment for WebGPU applications. Now we completed our first WebGPU project that shows how to set up development environment. This is project 2 of this video series. Here I will explain how to create a colorful triangle in WebGPU. As shown here, this is a colorful triangle. This project is based on our first project. You can open project 1 directly from Visual Studio Code or clone the source code from the GitHub repository git clone. This is a GitHub link for the project 1 source code. I also put this project 2 source code into the GitHub repository. Here is the link. So you can download the source code used in this project from this link. Now we will open the project 1 directly from Visual Studio Code. Here we first add a CSS file called site CSS to the src folder. Add a new file called site.css. Type some code into this file. Then just save and close it. Just like a WebGL. The first thing we need to do to use WebGPU for graphics rendering is to create a canvas element. From the dist folder, open index.html file. Here we need to change h2 element from here. Here we define canvas element with ID canvas WebGPU. Later, we will create WebGPU graphics on these canvas. The WebGPU programming consists of two parts. One is the control code written in TypeScript or JavaScript, and the other part is the CIDR code run on the GPU. Here we will use the official CIDR language for WebGPU called WGSL, which is short for WebGPU CIDR language. To take advantage of the code highlight in VS Code, we will convert the CIDR code with WGSL extension into TypeScript-like module. To do this, we need to install a CIDR loader for Webpack. Now open a new terminal window. Run the following command to install the CIDR loader called npm install ts CIDR loader. This loader was originally created for loading GLSL CIDR code, but we will make it works for WGSL here. Next, open the Webpack configuration.js file and add the following code to it. Here, the file with WGSL, GLSL, VS means vertex CIDR, FS means fragment CIDR. So the file with these extensions will be treated as CIDR code by this CIDR loader. We then need to install a WGSL extension from VS Code. Click this extension link, search for WGSL. Here is first one, WGSL, provide a syntax highlight. I already installed this module, so you can see here the code highlight. In this case, it's easy to write CIDR code, use this extension. So if you haven't installed it, just click this install button to install it. Next, we need to add some type declarations for our CIDR. Add a new subfolder to the src folder, new folder called types. Then add a new file called CIDR.d.ts file. Inside this file, we add some content to this file. Here we add declare module. So the file with WGSL, GLSL, VS, or FS, we declare this file as module. So right now we can save this file and close it. Now we can write our CIDR code. In the src folder, add a new file called CIDR.wgsl file. Then add some code. From this code, you can see that there are two CIDRs here. One is vertex CIDR and another is fragment CIDR. We have CIDR function for vertex is called VS main function. VS means vertex CIDR function. Here we have FS main fragment CIDR main function. The vertex CIDR takes vertex data, including word position, color, and texture as input. The output is the position in the clip coordinates, while the other outputs, such as color and texture, will be passed to the fragment CIDR. These values will then be interpolated over the fragments to produce a smooth color gradient. Now back to our example. In the vertex CIDR, we first define an output structure here that contains a built-in position and the output color we call the V color. Inside VS main function, we first define three vertices of our triangle. Use the floating point vector 2 vector, so we have three vertices. We also specify colors for each vertex. Use a floating point vector 3 vector. You can see the first one, the 1, 0, 0, this means red. The second color is 0, 1, 0 is green. The final is 0, 0, 1 is blue. So we define different color for each vertex. Next, we define output using the output structure here. We then convert the 2D vector of the position into vector 4, the 4-dimensional vector. We put a z component as 0 and a w component as 1. Similarly, we convert 3D vector for the color into vector 4. Here, the 1 represents the transparency of the color. In the fragment shader, we take the output color from the vertex shader as input and retain it as the fragment color. Okay, this is the shader we will use when create our colorful triangle in WebGPU. So now we can save this file and close it. Next, we will use TypeScript to write WebGPU control code. Open the main.ts file and replace its content with the following new code. Here we first introduce the check WebGPU function from help.ts file. Then from shader.wgsl file, we introduce our shader from this file. We also import the site.css file. Here we will use it to configure our web page layout. Next, we create a new function called createTriangle. This function must be an async, you can see async function, because WebGPU API itself is async. Inside this function, we first check whether your browser supports WebGPU or not. In WebGPU, we can access GPU by calling the request adapter here. Once we have this adapter, we can call the request device method to get a GPU device. This device provides the context to work with the hardware and an interface to create a GPU object, such as buffer and texture. We can also run commands on this GPU device. As with WebGL, we need a context for our canvas element that will be used to display graphics. Here we use the canvas element to request WebGPU context. You can see here, get context by the name WebGPU. This is a keyword used by WebGPU to create the context. We then configure this context with the device and format. Next, we define the render pipeline by calling the createRenderPipeline methods. Inside this pipeline, we have several attributes. The first one is the vertex, where we assign the shader to the module here with the entry point as a VS main function. This function is created in our shader file. Similarly, for the fragment attribute, we assign the shader to the module and the entry point as fs main function. Another required attribute is a primitive here. This attribute contains a field called topology. We set it to triangle list because we wanted to create a triangle in this project. Next, we create the comment encoder and render path by calling the beginning render path. This render path accepts a parameter of type GPU render path descriptor as a render path option. Here we only use color attachments. That is an array to store image information. In our example, it stores the background color in the clear value area. We have another field called load value. This field will be removed from WebGPU in next version, so we don't use it here. Next, we assign the pipeline to our render path and draw our triangle by calling the drawing method here. We call the AND function to finish current render path, meaning that no more instructions are sent to the GPU. Finally, we submit all instructions to the queue of the GPU device for execution. After running the command, our triangle will be written to the GPU context and displayed on our canvas element. Now we finish the implementation of our createTriangle methods. These methods provide basic procedure to create WebGPU applications. That is, first we initialize WebGPU API, create a seeder program, set up render pipeline, and build render path, call draw function, and submit instruction to the GPU for execution. Finally, we call the create triangle function to generate our triangle. Up to now, we have finished our programming for this project. We can now run the following command on the terminal window. npm run prod to bundle our TypeScript code in production mode. Okay, finished. Our bundle file created successfully. Now we can click Go Live link from here to open Chrome Canary to view our triangle. Click this link. Here is our colorful triangle. You can see here is red, green, and blue. From one vertex to another, you can see the color changes smoothly because the WebGPU interprets the color internally, which gives a smooth color gradient. Now we have completed project 2. This is project 3. We will create a colorful square using GPU buffer. In the last project, we create a colorful triangle in WebGPU by writing a vertex and color data directly in the seeder code. This approach is only possible for creating very simple shapes. It is almost impossible to use this direct approach for creating complex 3D graphics with different colors and textures. In this project, I will introduce GPU buffer and show you how to use it to store vertex and color information. In this example, we will create a colorful square to explain the concept of the GPU buffer. Here we will introduce several new concepts that will be the foundation to create complex 3D graphics objects. A GPU buffer in WebGPU represents a block of memory that can be used to store data for GPU operations. In this project, I will show you how to use the GPU buffer to store vertex position and color data. You can download the source code used in this project from this GitHub repository link. You can see we have a specific commitment version. This version is specific for our current project. Now let's start Visual Studio Code and open project 2 that we built in the last video. Okay, here's the project 2 we used in the last video. Now, let's first make some changes to the index.html file. From dist folder, open index.html file. Now we need to change here the h1 title to create square using GPU buffer. So we don't need to change the other part of the code, so we can save this file. Next, from src folder, open helper.ts file. Now we need to add a new function called init GPU to this helper file. So we need to add some code here. You can see we place our WebGPU initialization code to this function init GPU. So this can avoid code duplication because initialization will be same for all WebGPU projects. This function is an async function and it returns the device, canvas, format, and context, which will be used when we create render pipeline and render path. We also want to add another function called create GPU buffer to this helper file. So we need to add another function here called create GPU buffer. You can see this function takes 3 input, the device, the data, and the usage flag. Here we set the default uses black to vertex or copy destination. Here you can see we call the device create buffer a method to create a GPU buffer and set the size as the data, the byte length, to allocate the room for the buffer data. The other attribute here, mapped at creation, we set this attribute to true. This means that GPU buffer is owned by the CPU, which is accessible in read-write from TypeScript code. Once the GPU buffer is mapped, the application can ask for access to range of content with get, for example here, get mapped range method and set it to the data to be stored in the buffer. Please note the mapped GPU buffer cannot be directly used by GPU, and it must be unmapped used by calling the unmap methods. Here, our create GPU buffer method returns unmapped buffer, which can be used by the GPU. So be careful here about GPU buffers mapped and unmapped states. Now we can save this file and close it. Next, we need to make changes to the min.ts file. From src folder, open the min.ts file. And we need to replace its content with the new code. You can see here we first introduce the init GPU and create GPU buffer from helper.ts file. And then we introduce the seeder. The seeder code will be discussed in a moment. Inside the create square methods, we first call the init GPU method to create a GPU object and then get the device from it. Next, we define the vertex data and color data here. You can see these are vertex data and color data. Here is vertex coordinates of our square A, B, C, D. So the coordinates like here, A is minus 0.5, minus 0.5. This is A, B, D. We have divided this square into two triangles, A, B, D, D, B, C. The vertex of each triangle must be arranged in the counterclockwise order. You can see here A, B, D, D, B, C. We also assign a color to each vertex. You can see A is red, B green, C blue, and D is yellow. You can see here is for A is red, for B is green, and so on. These data are consistent with the coordinates source in this figure. Of course, you can also divide the two triangles in other way around. For example, A, B, C, C, D, A. So you draw the diagonal this way. So you get another two triangles. This doesn't matter. Next, we create two buffers by calling the create GPU buffer. One is a vertex buffer and another is a color buffer. Next, we create the pipeline by calling the create render pipeline methods. The new code we add here is for the buffer attribute. Before we don't have this the buffer attribute. Now it is a two-element array. The first element is for the vertex position. The second is for the color. You can see for the vertex position, we have array stride. We set it to 8. Since each vertex is represented using two floating 32 elements, each floating 32 number requires 4 bytes. While for the color, it is represented for each vertex using 3 floating 32 elements. So its array stride is set to 12. Another important parameter here is the seeder location. For the vertex position, we set the seeder location to 0, and for the color, we set the seeder location to 1. The other part of the code is very similar to that used in the previous project. Here we set the primitive topology to the triangle list. One new thing here is that after setting the pipeline to the random path here, we also need to set vertex buffer to the random path. Uses vertex buffer and color buffer. You can see here, set vertex buffer. At 0 slot is vertex buffer. At slot 1, we set a color buffer. In the draw function here, we set the number of the vertices to 6 because we have 2 triangles now. Now we finish the modification to this file. Now we can save this file. Next, we need to make modifications to our seeder code. From ICRC folder, open seeder.wgsl file here. We need to replace its content with new code. Here you can see we didn't define any vertices and colors in this seeder code because we store this data in GPU buffer. Instead, we introduce 2 inputs. One is at location 0 pulse and another the color at location 1. This must be consistent with the seeder location definition in the pipeline in our main.ts file. Because we define seeder location as 0, you can remember, for the position. And seeder location is 1 for the color. So here, position is 0, and here, color is location 1. This is how we set up the relationship between the vertex seeder and the GPU buffer. Now we define them here as a vector flow F32. For the color, same thing, vector flow F32. They look like not very consistent with the data stored in the vertex and color buffer, where for the position is a 2D array, and for the color is 3D array. This is because WGSIO seeder is smart enough to automatically convert them into a vector flow type by add 0 to Z component and 1 for the W component. You can see here we also define 2 outputs. One is position, one is V color. Use a structure. Inside this VS main function, we process the position and color data by assign the pulse to the position and color to the V color. Inside the fragment seeder, we introduce the V color from the vertex seeder and retain it as fragment color. Okay, this is the seeder we will use when creating our square. We can now see this file and close it. Now we can run the following command in the terminal window to bundle our TypeScript code. npm run prod to bundle our code in production mode. Okay, the bundle file is created successfully. Now we can click the Go Live link to open Chrome Canary to view our square. So click this Go Live link. Here is our colorful square with different vertex color. Here is red, green, blue, and yellow. From one vertex to another, you can see the color changes smoothly because WebGPU interpolates color internally, which gives a smooth color gradient. Okay, now we finish the project 3. In projects 2 and 3, I demonstrate how to create a triangle and a square graphics in WebGPU applications. In fact, these two objects are flat and 2-dimensional. We have not created any real 3D graphics yet. In this project 4, I will explain how to create a 3D cube with distinct face colors. This is the first real 3D object we are going to create in a WebGPU application. You can download the source code used in this project from this GitHub repository link. Here we have a specific version for this project. This example involves a lot of code and mathematics. So please get ready to digest it. In order to create a real 3D object in WebGPU, you need to have the math background of 3D matrix and transformations. Since our computer screen is two-dimensional, it cannot directly display 3D object. To view 3D object on a 2D screen, you have to project your object from 2D to 3D. That will involve a series of coordinate transformations. From here, you can see that we define 3D object in the object coordinate system here. We then perform various transformations on the object, including scaling, translation, and rotation. We call this transformation as a model transform. After this transformation, we convert the object in the object coordinates into the object in the world space. Next, the view transformation locates the viewer in a world space and transform our 3D object into camera space that also called eye coordinates. The purpose of the projection transform here is to define a view volume called view frustum. Like here, this is a view frustum, which is used in two ways. It determines how an object is projected on the screen. It also defines which portions of the object are clipped out of the final image. That is, only the portion inside this frustum will be kept, and anything outside this frustum will be clipped out. Finally, we use the view port transform to convert the clip coordinates into the normalized device coordinates. In WebGPU, the viewport transform here is automatically performed in the Cedar code. Please note that, like WebGL, the WebGPU API does not provide any functions for working with transformation. In this project, we will use a JavaScript package called GL Matrix to create 3D matrix operation and transformations. Since the 3D matrix and transformations are common for any computer graphics programming, here I suppose you already have this math background. I will not spend any more time on this. Instead, I will concentrate on how to create 3D objects in WebGPU applications. From this project, you will learn some of important concepts in WebGPU. That is, uniform buffer and banding group. We will use the uniform buffer to represent the transformation and projection matrices, and then use the banding group to pass the uniform buffers to the vertex shader. Now we start with our Visual Studio Code and open our project 3 that we built in the last section. Here is the code we used in project 3. First, we need to install a new npm packages called GL Matrix. npm install GL Matrix. And we will use this package to perform matrix operations and 3D transformations. Now, let's make some changes to the index.html file from dist folder. Open index.html file. Here we need to change the h1 title to cube with distinct face color. So we don't need to change other part of the code, so we can save this file. Here we are going to create our 3D cube, and these are the coordinates of our cube. From this diagram, you can see there are 8 vertices and 6 faces. If each face has a different color, each vertex will then have 3 different colors. For this vertex, for example, C, they have top face, front face, and right face, because this different face has different color. So the vertex C can have 3 different colors, depending on which face we talk about. Here is the front face, A, B, C, D. You can see A, B, C, D here. As we did before, we can now divide this front face into two triangles. One is A, B, C, C, D, A. These two triangles, you can see here, A, B, C, and C, D, A. In this way, you can perform triangulation for the other faces. Next, add a new TypeScript file, src folder, add a new file, vertex data.ts file. Add the new code to this file. Here is the position data for our cube. It's front face, right face, and 6 faces. This is the color data for the different faces. You can see front face will use blue color, right face is red, and back face is yellow, and so on. So different face has a different color. All the position coordinates and the color are consistent with this diagram shown here. Now we can save this file and close it. Next, we will make some changes to the seeder code. From src folder, open the seeder.wgsl file. Now we need to replace this content with the new code. You can see this feeder is different from that we used in Project 3 because we need to incorporate the uniform buffers that stores transformation and projection matrices. Here we define a uniform structure and then use the binding group to pass the model view projection matrix to the seeder. Here the MVP matrix means model view projection matrix. You can see here the variable type is uniform. Next, we define the output structure as we did in the last project. Is define position and V color. This is the same as before. For the VS main function, we also define the two input. One is position, one is color. It's the same as the last project. And inside this function, the only difference is the position not only has the pulse here, but we also multiply by this model view projection matrix. So perform the transformation on this position. For the fragment seeder, we still use the V color as input and retain it as a fragment color. This is the same as in the project 3. Now we can save this file and close it. Now we open the help.ts file from src folder. Here we first need to import from GL matrix. We need to introduce the vector3 metaphor and then add a new method called create view projection to this file. This method create view projection takes 4 input arguments. First, the aspect ratio, the camera position, camera look at direction, and the camera up direction. Here we first create a view projection and a view projection matrices. We then use a metaphor perspective and a metaphor look at to create a projection and a view matrices. Next, we use metaphor multiply methods to combine projection matrix with view matrix to form our view projection matrix. This function returns view matrix, projection matrix, a view projection, and a camera option. The camera option will be used in the next project when we discuss the camera control. Now, we need to add another function called create transformation. This is used to construct a model matrix. Here, we first create 3 rotation matrices for rotation about x, y, and z axis. We then create a translation and scaling matrices. Next, we perform individual transformation for the input arguments here. Finally, we combine all transformation together to form our final transform matrices, which is our model matrix. Now, save this file and close it. Next, we need to make some changes to the main.ts file. From src folder, open main.ts file. Here we need to replace its content with the new code. Here we first introduce some methods from help.ts file, including the newly create transforms, create view projection. We also introduce the cube data from the vertex data.ts file, as well as matrix 4 from GL matrix library. Inside this create 3D object methods, the code is very similar to that we used in the project 3. Here we create the vertex buffer, you can see, and color buffer using cube data position and cube data colors. Here the pipeline code also similar to the project 3. The difference is here array stride for the position is 12 instead of 8. Right now for the cube we have x, y, z coordinates, so we have 12 here. For our color still 12 because we have RGB elements. Here we also set seed location to 0 for the position and seed location is 1 for the color. The only difference in the pipeline here is we add this depth stencil attribute. Here we set depth right enabled to true to enable the depth stencil testing. The depth stencil testing determines whether or not a given pixel should be drawn. For 3D graphics, enabling depth stencil testing is very important. Otherwise, you may get unexpected results. The following code is new and specific to our 3D cube. Here, we create a model of view and model view projection matrices by calling the create view projection methods. We then create a uniform buffer for our MVP matrices. You can see here the usage we set is uniform for our transformation. The size is 64 since our matrix is 4 by 4. So we have 16 elements. Each element is a floating 32 number, so its size is 64. We then define the binding group by calling create binding group for this uniform buffer. Here we set the layout as a default pipeline get binding group layout 0. This means we use the binding group 0 layout. In the entrance attribute, we set the bindings to 0 and set buffer here to the uniform buffer we just defined here. If we have more uniform buffers, we can add the elements here put into this entrance array. In addition to the texture view from context, we also introduce the depth texture. Here we set the size as our canvas width and height. And format we use here is depth 24 plus. You can also use other format. The usage here we set render attachment. Now our render path description including two parts. One is color attachments and other part is depth stencil attachment. The color attachment is the same as we use in the project 3, but the depth stencil attachment is specific for our 3D cube. Next, we construct the model matrix by calling create transform method defined in the help.ts file. We then obtain model view MVP matrix by multiply the model matrix to the view projection matrix. So we got the final model view projection matrix. And then we add this model view projection matrix to our uniform buffer by calling write buffer methods. You should already be familiar with the following code here. We just define render path and set vertex and color buffer. But we also need to set the binding group here. Use uniform binding group. which is needed to pass the uniform buffer to the vertex seeder. Now we finish the modification to the min.ts file. We can then save this file. Up to now, we have finished all the programming for this project. Then we can run the following command in the terminal window to bound our code in production mode. npm run prod. Okay, the bound file is created successfully. Now we can click the Go Live link to open Chrome Canary to view our 3D cube. Click this link. Here is our cube with distinct face color displayed on this page. Okay, we have finished this project. This is a project file in which we will discuss the animation and camera control. In the last project, I explained how to use the uniform buffer to create a 3D cube. In this project, I will illustrate how to animate that cube and how to use mouse to interact with the cube. You can download the source code used in this project from this GitHub repository link. Here, the specific commit version is used for this project. For animation, we will use the JavaScript request animation frame function. This function can make changes to your screen in an efficient and optimized manner. Here is an example of using request animation frame. You can see here we loop over and over again use recursion. Here we first define the DOM element in the UI and define a start number of 0 here. Next, we create a count function that increases number by 1 and then set it as a text content for the counter element. Inside this counter function, we call request animation frame and pass the counter function itself as the callback function. This causes it to run again just before the next frame. Finally, we use the request animation frame function to start the animation. This is the basic usage of the request animation frame. For using the mouse to interact with the cube, we will use the npm package called 3D View Controllers. This package can be used to control camera with your mouse. You can then interact with 3D object by controlling the camera. Now let's start Visual Studio Code and open Project 4 that we built in the last section. Here is the code used in Project 4. First, we need to install JavaScript package called 3D View Controllers. Open terminal window and run npm install 3D View Controllers. We will use this package for camera control. The package is already installed. Now, let's make some changes to index.html file from dist folder. Open this file. First, we need to change h1 title to animation and camera control. We also need to add 2 radio buttons that let you select whether you want animation or camera control here. You can see the video button. Okay, now we can save this file. The seeder code in this example is the same as that used in the project 4, so we don't need to make any change to the seeder code. Now, from src folder, open help.ts file. Here we need to add a new method called create animation. We need to add a create animation here. This is the code for create animation methods. Here, the draw argument is the callback function. Here we want to animate the rotation around x, y, and z axis. Use the step function here, the step function. The create animation has a boolean argument here is animation. that controls whether you want to animate the object or not. Now, we can save this file and close it. Next, we need to make some changes to the min.ts file. Open min.ts file. We need to replace the content with the new code. This code actually is very similar to the code used in the last project. Here, in addition to the other function introduced from help.ts file, we also introduce create animation function, which just created. Note that we use here require to introduce 3D view controls module instead of the import. This is because the 3D view controls package was created using old modules approach. So we have to use require instead of import here. Here we define create camera from this package. In the create 3D object method, we introduce an input argument is animation, and we set its default value to true here. Here, initialization code and pipeline code are the same as those used in the last project. We don't need to make any change to this code. In the creating a uniform data section, we define V matrix. This view matrix. This is the new matrix. Next, we need to add rotation and camera. Rotation we define use vector 3, and camera we define create a camera here. They have argument carriers and camera option. We don't need to make any changes to the code for creating uniform buffer here and a uniform binding group. This is random path description, also same as that used in the last project. Here we put this random path related code inside a new function called draw function. This draw function is defined as a callback function for our animation. You can see here, if is animation is not true, we use the camera to generate our view matrix, and then multiply projection matrix with this view matrix to form our view projection matrix. The rest code of the draw method is the same as that used in the last project. Here we start animation by calling the create animation function. You can see we have a callback function, use the draw function defined here. Finally, we need to add the radio button selection here. You can see that if the radio checked value is equal to animation, we run animation. Otherwise, we use the camera control. Now we finish the modification to the min.ts file, so we can save this file now. Up to now, we have finished all the programming. Now we can run the following command in the terminal window. npm run prod to bound our TypeScript code. Okay, the bound file is created successfully. Now we can click the Go Live link to open Chrome Canary to view our 3D cube. Click this Go Live link. You can see the animated cube on this page. It is rotated continuously because we call the animation mode. Now you can click on this camera control radio button here. Then you can use your left mouse button to rotate the cube and use the right button to move around. And you can also use mouse wheel to zoom in, zoom out the cube. So you can use the mouse to interact with the cube. So now we have completed this project. In the previous several projects, I explained how to create some 2D and 3D objects. However, when rendering this graphics object with solid colors, you may find that the image looks flat and is failed to illustrate the 3D nature of the object. This is because we neglect the interaction between light and surface in our objects. Lighting helps provide visual effect to a scene so that it looks more realistic. Lighting is one of the most important factors for creating real-world seated 3D graphics objects. However, WebGPU does not provide much built-in features on lighting. It just runs two functions, vertex and fragment shader. If you want the lighting effect in your 3D scene, you have to create the lighting model yourself. In this project, I will build a simple lighting model in WebGPU and use it to simulate the light source. Here you can download the source code used in this project from this GitHub repository link. Here the specific commit version is used for this project. Here I will discuss three types of light sources: ambient light, diffuse light, and specular light. The ambient light is the light that illuminates all objects uniformly, regardless of their location or orientation. It is a global illumination in an environment. The diffuse light and specular light reflection depends on the angle of the light to a surface. When the light hits the surface, the diffuse reflection occurs in all directions as shown here, while the specular light reflection occurs in a single direction as shown here. Here shows the light reflection on a torus surface. On the left here, the light only from ambient light. You can see the torus looks very flat. Here in the center shows light from both ambient plus the diffuse light. You can see the 3D feature already shows here. On the right here, have three light sources: ambient plus diffuse and plus specular lights. You can see this torus looks more realistic. So this is the light model we want to build in this project. The light reflection depends on the angle at which the light hits the surface. The angle is essential to the diffuse light and the specular light. This angle is always associated with the surface normal that is perpendicular to the surface. To build a light model, we need to calculate the surface normal based on the direction in which the surface is facing. Since the surface of a 3D object can be curved, it can face different directions at different vertices. So a normal vector is usually different for different vertices. That is, normal vector is always associated with a particular point on a surface. Here shows normal vector for a 3D cube. Here the front face is pointed toward the screen, so its normal vector is 0, 0, 1. The right face is facing direction to the right, so its normal is 1, 0, 0. And the top face is face toward the top, so its normal vector is 0, 1, 0. So similarly, you can specify the normal vectors for the back, left, and bottom faces. Note that the length of the normal vector should be always 1. That is, we need to normalize the normal vectors. For a general quadrilateral A, B, C, D, its 4 vertices may not in the same plane. We can divide it into 2 triangles, A, B, C, and C, D, A. We can calculate its surface normal in 2 steps. First, we calculate the weighted normal for each triangle, which is weighted by the area of that triangle. The triangle with larger area will get more weight. As we know, the area of a triangle is proportional to its cross product of 2 sides. For example, here, for triangle A, B, C, we have cross product BC and CA, BC, and CA. Similarly, for the triangle CDA, we have cross product DA and AC. The next step is to calculate the surface normal from the weighted triangle normals. That is, the surface normal equals the sum of two weighted normal, and we can then normalize it. So we get this quadrilateral normal equals normalize this two cross product, the sum. This one triangle plus another one. So we can combine these two terms to form one term equals cross product CA and DB. So this means the surface normal for this general quadrilateral just equals the cross product of CA and DB, just equal to the cross product of these two diagonal vectors. We will use this formula to calculate the light model for our 3D surfaces. Once we have calculated the normal vector, we can use it to compute the light intensity. For diffuse light, its intensity is proportional to the cosine between the light vector here and the normal vector n. You can see here the cosine alpha equals normalized L dot n. Here, if we define the ID, the diffuse intensity, KD, the diffuse material property, so we can have this formula. The diffuse intensity equals KD times maxima cosine alpha and 0. Here, the maximum is used to avoid the negative value of the cosine alpha here. We only take the positive value. We can also add the ambient light to the diffuse light intensity like this. Here, IA is the ambient intensity, so the total light intensity is maxima KD, and here is IA. So we add the ambient intensity to this diffuse light like this. For specular light, we have two models. One is a foam model. This model is very simple. So the RS, the intensity of specular light, equal to Ks, Ks specular material property, and S is the thinning of the surface or roughness. The V is the view direction, R is reflection direction. One issue with the foam model is that the angle between the view direction and the reflection direction has to be less than 90 degrees in order for the specular foam term to contribute. We can use the Berlin foam model to address this issue. Berlin foam model uses a different set of vectors for its computation based on the half angle vector. Here's the half angle vector. You can see L is the light direction, N is normal vector, V is the view direction, H is the half angle vector. Define L is light direction plus the view direction. The view direction plus light direction, it gives the H here. The formula in a Berlin foam model becomes N dot H instead of V dot R here. So the angle between this N and H is always less than 90 degrees. So this N dot H always give positive value. So we will use this Berlin foam model in our calculation for the specular light. Now let's go to the programming part. We start with Visual Studio Code and an open project file that we built in the last section. Here is the code for our project file. Now let's implement the light model in the Cedar code. From SRC folder, open the cedar.wgsl. We need to replace its content with the new code. Here we first define the uniform structure here that contains view projection matrix, the model matrix, and the normal matrix. Here the normal matrix is the transformation matrix for the normal vector data. When apply a transform to a surface, we need to derive the normal vector for the resulting surface from the original normal vectors. In order to transform the norm vector correctly, we don't simply multiply them by the same matrix used to transform our object, but we need to multiply them by the transpose of the inverse of that matrix. Since the current WGSL version does not implement the matrix inverse function yet, so we have to make this transpose of the inverse of the transform matrix in TypeScript code and then pass it as a uniform matrix as shown here, normal matrix. We then define an output structure that contains three variables: period in position, the v position, the position after some transformation we call the v position, and v normal, this normal vector after transformation. In our v as mean function, it contains two input arguments. One is vertex position called pose, and one is normal vector data. Inside this function only perform model transform on the position. This gives v position here because it is used in the light calculation. The v normal is the result of normal vector data multiplied by the normal transform matrix here. And the default position here is obtained by perform model view and projection transform on the vertex data. For the fragment seeder, we first introduce a uniform structure called frag uniform that contains two variables. One is the light position or light vector, and the other one is I position or the view vector. Also has another structure called light uniform. Here contains parameters for our light model. Here is light color and specular color. The specular light can have its own color, and other parameter contains ambient intensity, diffuse intensity, specular intensity, and specular sanitness. Here, the fs main function takes the v position and v normal as its inputs. Inside its function, we calculate the light model. Here is diffuse, just use n.l is cosine alpha. For the specular light, we use Blaine-Feng model is n.h. The output color from fragment seeder will be weighted, you can see, by ambient, diffuse, and specular light. Is a combination gives the final color. So this is the seeder we are going to use to calculate the light model. Now we can save this file and close it. Next, in the src folder, we will add a new TypeScript file called light.ts. Add a new file, light.ts file. Here is the code for this file. Here we first create an interface named light inputs that contains the parameters used for calculating light model. This code also contains the new function create shape with light, which has 4 input arguments. One is vertex data, normal data, and light input, and is animation parameter. Here we set the default light parameters if no parameters were passed, so they have some default value for the light parameter. Next, we create a vertex buffer and a normal buffer here. You can see that the pipeline contains a buffer attribute here. It is an array, contains 2 elements. The first element is the vertex data, with the seed location being 0. The second element is for the normal vector data, with seed location being 1 here. The other part of the pipeline is the same to that we used in project 5. Next, we create uniform data. Here we define normal matrix and model matrix, and view projection matrix here. For simplicity here, we set the I position we get from the camera equals I position. This means light vector is equal to the view vector. Here we then create 3 uniform buffers. One is a vertex uniform buffer, another one is a fragment uniform buffer, and finally is a light uniform buffer. The vertex uniform buffer is used to store the model matrix, view projection matrix, and normal matrix. The fragment uniform buffer is used to store the eye position and light position. And the light uniform buffer is used to store the light parameter, which will be used in calculating the light model in the fragment shader. Please note here, inside this callback draw function, we write model matrix and normal matrix inside this draw function because we want to use the real-time model matrix to perform various transformations. Not we construct the normal matrix here. We first invert this model matrix and then transpose this normal matrix and get the final normal matrix. That means we do the inverse and transpose on the original model matrix and finally get the normal matrix. When we set the data to the buffer, please note here is 64 and 128 is the offset. So we also need to use the correct offset to write this data to the uniform buffer. Finally, we set the vertex buffer, normal buffer, and the uniform binding group to the render path. Now we finish the coding for this file. We can save this file and close it. Okay, we complete the programming for calculate the light model. In next project, we will use the light model implemented here to create a 3D cube with the lighting effect. In project 6, I explained how to build a simple light model in WebGPU. In this project, I will show you how to use this light model to add lighting effect to a 3D cube, as shown here. You can download the source code used in this project from this GitHub repository link. This specific commitment version is used for this project. Now start Visual Studio Code and open our project 6 that we built in the last section. Here is the code used in project 6. As we discussed in the last section, in order to calculate the light model, we have to know the normal vector at each vertex on the surface of the 3D object. Now we need to add normal vector data to the vertex data of our cube. From SRC folder, open the vertex data.ts file. Here, for the cube data methods, we need to add a normal vector data here. You can see that vertices on the same face have the same normal vector. For example, the front face all has 0, 0, 1. Similarly, for the right is 1, 0, 0, 1, 0, 0, or the 1, 0, 0, and so on. Once we add the normal vector data to this cube data function, we need to return the normal data. Here's normals. We also need to return normals. Okay, now we can save this file and close it. Next, we need to make some changes to the index.html file. From the DRST folder, open the index.html file. Now we need to replace its content by the new code. Here we add some input parameters here that let you test our light model. This parameter also allow you specify object color and ambient, diffuse, and specular light coefficients. You can also specify the surface sameness and specular color for the specular light computation. Now we can save this file. Next, we need to make some modifications to the min.ts file. From SRC folder, open min.ts file. Now replace its content with new code. Since most code for render pipeline and render path have been already included in the light.ts file, Here the mean.ts file becomes very simple. First we introduce create shape with light and light input interface from the light.ts file. And then introduce the cube data from vertex data.ts file. Next, we call the cube data methods to get the vertex data and define the default parameter. Here, light input, we just use the default parameter. And also is animation, we set it to true. And then we call the create shape with light function to create a 3D cube with lighting effect. This part of the code allows the user to recreate the cube with different lighting effect by change the input parameters. Now we finish the modification to the mean.ts file. We can now save this file. Now we can run the following command in the terminal window to bound our TypeScript code. In production mode, npm run prod. Okay, the bound file is created successfully. Now we can click the Go Live link to open Chrome Canary to view our 3D cube with the light effect. Click this link. Here is the red cube with the lighting effect displayed on this page. We can make some changes to the input parameters and click the redraw button to recreate the cube. For example, we can set the diffuse and specular coefficient to 0 here, to 0 and 0, and ambient light to 1. Now click redraw. We get a cube with ambient light only. You can see the cube looks flat and no 3D feature. Now let's add diffuse light and specular light back. Diffuse 0.8, 0.4, and 0.2, for example. We can then change the color of the object. For example, this red, we change it to green 010, and also change the specular color from white to yellow. And then click redraw button. You can see here the yellow. You can increase the thickness, for example 100. You can see the spot a little bit yellow with specular light. Now go back the animation. So by changing this parameter, you can get new lighting effect on this cube. You can use this light model to easily create your own 3D object by following procedure presented here. Okay, now we have completed project 7. The projects we discussed so far will apply a fixed color by assigning a desired color value to the fragment color variable in the fragment seeder. In this project, I will explain how to use the color map to render 3D surfaces. Surfaces play an important role in various applications, including computer graphics, games, and 3D data visualization. In some graphics and chart applications, we need a custom color map to achieve special visual effects. In fact, the color map is just a table or list of colors that are organized in some desired fashion. We can create a custom color map with an M×3 color matrix, with each rule representing RGB values. The rule index can represent the Y data of a 2D chart or height of a 3D surface plot. For a given color map matrix, the color data values can be linearly scaled to the color map. Here shows the color strips for the color maps that we will create in this project. You can see that each color map has a familiar color map names such as Edge, SV, Hard, Cool, and Jazz, and so on. You can download the source code used in this project from this GitHub repository link. This specific commit version is used for this project. Now start with Visual Studio Code and open our project 7 that we just built in the last section. Here contains the source code used in the last project. We can easily create a custom color map using simple mathematical formula. Here I will provide several commonly used color maps using M/3 color map array. Now add a new TypeScript file called colormapdata.ts file to the SRC folder. So in SRC folder add a new file called colormapdata.ts file. And then add a new method to this file. Here, the color data methods contains the 11 different color maps data. You can see HSV, heart, and jazz as default. Inside this function, you can see each color map contains 11 RGB color arrays. Each array here is RGB value. Here shows the color strip generated use this color map data. This RSV corresponding this color strip. So here is the jet corresponding this color strip. So these color strips are generated use this color map data. In the color map data function, we assume these 11 color arrays are uniformly distributed in the range of 0 and 1. For example, the color 0, this first element, represents a color at 0 location, while colors 5 represent a color at 0.5, etc. However, we have to use the interpolation method to get a color at, for example, 0.55 or any other arbitrary locations. So here we will use an npm package called interpolate arrays to do the color interpolation. Now in the terminal window, we run the command npm install interpolate arrays to install this package. Now at the top of this color map file, we need to introduce this package here. Here you can see again, we use require to introduce this package because was created originally using the old modules methods. So we have to use the require instead of import to get this package. Next, we add a new function here called add colors. Here is add colors methods to this file. This function accepts the x argument whose value is in the range of minima and maxima. This function allows you to interpolate a color for any arbitrary x value. Inside this function, we first get the color array by calling the color map data methods with the color map name as input, and then make sure the input x parameter is in the range minima and maxima range. Next, we normalize x to the range of 0 and 1. Finally, we interpolate the color for the x variable by calling the interpol here, the color, and normalize x here. This interpol comes from the interpolate arrays package. Now this function returns RGB array with each component being in the range of 0 and 1. So now we can save this file and close it. Next, in the SRC folder, rename light.ts file to the surface.ts file. So we rename this file to surface. This surface.ts file will be used to create different surface plots First, we need to make small changes to the light input interface. Here, we can remove the color field here because we don't need to specify the solid color for our object, but we will use the color map for the object color. Then we add a new field called is two-side lighting. Since 3D surfaces are usually open surfaces, we need to implement the light model for both the front and back sides in order to see the surface clearly. But this parameter controls whether you want one-side or two-side lighting. Next, we change the function name here. Create surface with color map. So we change create map. And then add the color data as its input argument. Here we have normal data. We need to add color data. This color data means color map data. Here we need to remove this color and add a new default value for the two-side lighting here. Here we set the default value 1, it means the two-side lighting. If it's 0, it's one side. Here we create a vertex buffer, a normal buffer. We also need to create the color buffer here. Color. And use color data. Next, here is buffer, the array is first the vertex buffer, this normal buffer. We also need to add another buffer for the color map data. So here we need to set the seeder location to 2. We don't need to change the other part of the code for the pipeline. So other part is the same as that used in the last project. The code for the uniform data, camera, and uniform buffer layout is the same as that used in the last project. So we don't need to change anything here. But here, the light parameter, we need to make some changes because the light color we already removed. So we remove this light color. But we need to add another parameter is called is two-side lighting parameter. So we need to add the parameter here. It puts is two-side lighting parameter, but 0, 0. But we will make the parameter consistent is a vector 4 array. The other thing we need to make a change is that we should add the color buffer to the render path. We have vertex buffer and a normal buffer. We also need to add color buffer here. This is called color buffer x slot 2. Okay, we finished the modification to this file right now, so we can save this file. Next, we need to make some modification to the seeder code because we want to incorporate lighting and the color map into the seeder. So now from SRC folder, open the seeder.wgsl file. From this, open this file, and we need to replace its content with new code. This seeder is very similar to that used in the last project. Inside our vertex seeder, in addition to the vertex position, you can see, and the normal vector, we also add the color at location 2 to this input. Within the VS main function, we process the color map and assign this color map to the V color. In the fragment seeder here, we use the processed color map data as our object primary color. Here you can see V color is processed from vertex seeder. We use it as a primary color to get a final color. Inside the fragment seeder, the main function, you can see here the is two-side lighting parameter. Here is called the parameter 0. Control whether the lighting is applied to one side or two sides of our surface. We're setting it to 1 for two-side lighting, which is also default setting. For two-side lighting, you can see this for one side, for front side, we diffuse we use n.l. Specular light, we use n.h. If two-side lighting, we add another term here. For the diffuse, we use -n.l. For the specular, we use -n.h. This means for the backside light, we just reverse the normal vector to get the light for the backside. Now we can save this file. Okay, now we finished the programming for Colormap in this project. In the last project, we discussed the Colormap model. In this project, I will explain how to use this model to build simple 3D surfaces. Here is an example of 3D simple surface created using a pix function. Mathematically, a surface draws a y function on a surface for each x and z coordinates in a region of interest. For each x and z value pair, the simple 3D surface can have at most one y value. We can define a simple surface by the y coordinates of a point above a rectangular grid in the xz plane. The surface is formed by joint adjacent points using straight lines. Typically, the surface is formed using rectangular mass grids. However, WebGPU only provides triangles as the basic units to represent any surface in 3D. In order to represent a surface using traditional quadrilaterals, we need to write our own functions. You can download the source code used in this project from this GitHub repository link. This specific commit version is used for this project. Now start Visual Studio Code and open Project 8 that we built in the last section. Here shows the code used in the Project 8. First, we need to add a new TypeScript file called surface-data.ts to the src folder. Add a new file called surface-data.ts. We need to introduce vector3, import vector3 from geometrics library, and also need to import from Colormap data.ts file. Introduce add colors function. First, let's add a utility function called normalize point. That will be used to normalize the point to the range of -1 and 1. So we need to add a function, normalize function. You can see here, this function takes 3D vector 3 here, the points, x data range, x minima, x maxima, y minima, y maxima, z minima, and z maxima, and also introduce a global scale, a parameter that allows you to change the value range for the x, y, and z coordinates. This will be convenient for setting the default size of our surface. This function returns the normalized 3D point for our simple 3D surface as shown here. This surface can be formed by quadrilateral mass grid. Here is one of the quadrilateral. This can show in here. This unit grid cell. This unit grid is quadrilateral with 4 vertices, P0, P1, P2, and P3. We can divide this quadrilateral into 2 triangles, P0, P1, P2. This is one triangle. Another triangle is P2, P3, and P0, as shown here. We will create the vertex data, normal vector data, and Colormap data for this quadrilateral. Now we can add a new function called createQuad. You can see here that this function takes 4 points, just as shown here, point 0, 1, 2, and 3. Take these 4 points as its inputs, arguments. It also takes the y data range, y minima and y maxima, as well as the Colormap name as its input parameters, because we want to add Colormap to the y values for our surface. Of course, you can Colormap the data value in the other direction, such as x and z direction, but we usually add a color map to the y values. Here, we first create a vertex position data for the 6 vertices. This is point 0, point 1, point 2. This is the first triangle. This is a second triangle, point 2, point 3, and point 0. So this is the vertex for this unit cell, for these 2 triangles. Next, we define the normal vector for this quadrilateral. We already discussed how to obtain the normal vector for this quadrilateral in the previous project. It is simply equal to the cross product of these 2 diagonal lines of this quadrilateral. Here we introduce these 2 lines. First is P2, P0. P2, P0, we call the CA. Another line, P3 and P1. P3, P1, we call the DB. Then we get the cross product, we call the CP, these 2 lines. Then we normalize this CP cross product. We get the normal vector for this quadrilateral. So all the vertices on this quadrilateral have the same normal vectors. Next, we add the color map data to vertices for this quadrilateral. You can see the P0, P1, P2, and P3. This is the color map data for these 4 vertices. For P0, you can see we add the color map data to it by calling add colors function with its y component P01 and use the y data range, y minima and y maxima. The add colors function was implemented in the last project. If you want to add color map data to the other direction, for example, the x direction, you should use x, the data range, and also P0 here inside should be 0, this x component. Similarly, we add the color map data to the other 3 vertices. Finally, we add this color map data to these 2 triangles. These have 6 vertices. They have different color map on different vertices. Finally, create a call function returns vertex, normal, and color for this unit grid. This create call function here only creates the data for a single unit grid. Now we need to create data for the entire surface. We need to add a new function called simple surface data. This is a function create the data for an entire surface. This function takes f here. This input argument f is a math function that describes the 3D simple surface. We then define the data range in the xz plane. Use the minimum and maximum value for the x and z. Next, to input parameters n, x, and nz represent the grid divisions along the x and z directions. Here, the scale is a global scaling parameter used in the normalized point function. The scale y parameter is used to control the y value height relative to the x and z value. That is, scale y parameter here controls the aspect ratio of our surface plot. Inside this method, we first define the size of unit grid. You can see dx and dz. We then calculate the vertex position on our surface by calling the function f. You can see use this for loop. Inside that, we call the f, x, z function. This describes our surface. Here we also calculate the y value range. Y minima 1, Y maxima 1. Next, we reset the Y value range, use the scale Y parameter here. Next, we normalize vertex position by calling the normalized point using the value range for X, Y, and Z, and also the scale. Inside this double for loop, we first define the unit cell P0, P1, P2, and P3. This is a unit cell. And then call the create call function to get the vertex position, normal vector, and color map data for this unit grid. So this vertex, normal, and then color for our surface. Finally, this simple surface data function returns the vertex data, normal data, and color map data. Now we finished the programming for 3D simple surfaces in this project. In next project, we will use this framework to create a 3D Sinc surface with both the lighting effect and color map. In last two projects, we discussed the color map model and simple 3D surface construction. In this project, I will explain how to use the color map model and the simple surface data function to create a 3D Sinc surface. As shown here, this pretty Sinc surface we want to create in this project. You can download the source code used in this project from this GitHub repository link. This specific commit version is used for this project. Now start with Visual Studio Code and open our project 9 that we built in the last section. Here is the code used in the last project. First, we need to make some changes to the index.html file. From the dist folder, open index.html file. Here we need to change this h1 title to Sinc Surface. And then we need to change the parameter here. You can see here we have a two-side light parameter that controls whether we want to apply the lighting effect to one side or two sides of the surface. Here is a drop-down menu for the color map that contains 11 color map names we defined in the color map data.ts file. So you can select different color map for our surface from this drop-down. Here is the scale parameter that let you set the default size and aspect ratio for the Sinc surface. Now we can save this file. Now let's define our Sinc function. Add a new TypeScript file called mathfunc.ts file to the src folder. src folder, add a new file called mathfunc.ts file. Here is the definition of the Sinc function. Here R defined as square root x squared plus z squared. This function equals to sin r over r if r not equal to 0. Otherwise, if it equal to 0, this function equal to 1. In fact, this function is a Fourier transform of the rectangular function. Now we add some code here to define this function. You can see this function is very simple. It takes x and z and center parameter here as its input arguments. The center parameter here lets you set the location of our Sinc surface. Inside this function, we define r, use this formula as shown here. So here let y r equal to 0, this function equal to 1. Otherwise equal to sin r over r. This function returns a vector 3 point on the Sinc surface here. Now we can save this file and close it. Next, we need to make some changes to the main.ts file. From src folder, open main.ts file. Now we need to replace the code with the new code. Since most code for render pipeline and render path have been already included in the surface.ts file, so the main.ts file here becomes very simple. Here we first introduce the simple surface data from surface data.ts file, and then we introduce the Sinc function from mathfunc.ts file. Next, from a surface.ts file, we introduce create a surface with color map and also introduce a light input interface from this surface.ts file. Next, we create a new function called create a surface. This function takes light inputs, age animation, and a color map name, and a scale y as its input arguments. Inside this function, we call the simple surface data with, you see here, the Sinc function as the input argument. From this simple surface data method, we can get the vertex position, normal vector, and color map data. We then call create surface with the color map function to create our Sinc surface with the lighting and color map effects. And here we define the default input parameters, and then we call create surface a function to create a 3D Sinc surface with the default lighting and color map effect. This part of the code allows the user to recreate the Sinc surface with different input parameters. Here, this code allows the user to select the different color map from the drop-down menu. Now, we finished the modification to the min.ts file. We can save this file. Now we can run the following command in the terminal window to bound our TypeScript code. Open a terminal window and run the command npm run prod to bound our TypeScript code in production mode. Okay, the bound file is created successfully. Now we can click this Go Live link to open Chrome Canary to view our Sinc surface. Click this link. Okay, here is our Sinc surface with the default two-side lighting and jet color map displayed on this page. Now let's check what happens if we use one-side lighting. So we use camera control. This one side we set to 0. Control. You see the back. There's no diffusion and specular light on the back, but only has a very weak ambient light here. If we set it to 1 back, you can see the back. The difference, the one side and the two side, you have light on the back. Here, the scale set the default size of the surface. For example, we change it to 1, you get a smaller surface. Here, change it to 3, you will get big surface. So they can control the default size of the surface. We go back to 2. And here, the scale Y lets you control the aspect ratio. For example, we set it to 0, you get a taller surface, and change it to the 0.5, you get a shorter and fatter surface. So we change it to 0.3, so you can use this parameter to control the aspect ratio. Next, we can change the color map from this drop-down menu. For example, the item, bound, cool, Cooper, gray, hot, HSV, spring, summer, and winter. So you can get a different color map for our surface. You can see that in WebGPU, we can easily create a beautiful 3D surface with lighting and color map effect. You can create your own surface by simply provide your own math functions. So now we complete our project 10. You can use WebGPU to create advanced graphics in your web applications. Here are some more examples from my recently published book, Practical WebGPU Graphics. Here are some of parametric 3D surface examples. They all look beautiful because they have both color map and lighting effects, as we did for the simple 3D Sinc surface in our projects. Here are texture map examples on 3D objects. Texture plays an important role in 3D graphics. The modern GPUs have support for image texture built in on the hardware level. Texture mapping on 3D objects provides a more interesting and realistic look. These examples demonstrate that you can do texture mapping on sphere, cylinder, and 3D surface. You can also use multiple textures on 3D object. You can see here, each face of our 3D cube has a different image texture. Here are examples of domain coloring for functions with complex variables. These beautiful pictures are drawn pixel by pixel based on bitmap render, which is a computation-intensive process. Here we perform all calculations and render directly in GPU, which makes it possible for our real-time animation here. This is impossible in CPU. These are 3D fractal examples. They provide more structures than 2D fractals. Again, these nice pictures can be only created in GPU. In CPU, it is too slow and impossible to have this real-time animation. Here are some examples for large particle systems. This is compute boards, and we try to simulate the flocking behavior of boards. This picture shows particle kinematics with collision to the wall. This shows 3 mass centers that attract particles. Here we use compute shader to perform physics-related computations and update the positions and velocities on each frame. This is only possible in GPU for simulating this large particle system in real time. If you want to learn how to create these pictures and particle systems, please visit my website at drsu.net.com and my YouTube channel at Practical Programming with Dr. Su. Thank you for watching.